Here are some values for kernel and bulk densities of different grains. Again, you can see most kernel densities are in the range of 1.1 to 1.3 grams per cubic centimeter. So the dry matter in the grains has the starches and proteins and so on all have similar densities. The bulk densities, again, can vary with the type of grain, from the smallest for oats, 412 kilograms per cubic meter, or 32 pounds per bushel, up to the heavier grains like soybeans and wheat with 60 pounds per bushel, or 772 kilograms per cubic meter. You may have heard the term hardness with regard to corn kernels. Certainly, you've probably heard of soft wheat and hard wheat and the difference in kernel properties there. This is similar to that in that for corn hardness, we're talking about the proportion of translucent or hard endosperm in the kernel to the overall kernel volume. So if we have a large amount of translucent endosperm, a large proportion of that, then we'll have a harder kernel. This is important from the standpoint that it affects breakage susceptibility. Usually the harder kernels will be more resistant to breakage and dry milling quality. The harder kernels tend to give better yields of what we call flaking grits during the dry milling process, and that's desirable for the dry milling industry. They like to have large flaking grits because they can always make smaller grits from the large ones, but they certainly can't make larger ones from small ones. Porosity has to do with the amount of airspace in a container that's filled with grain. Basically, it's just the percentage of the total container volume that's occupied by air as opposed to grain. This affects things like the resistance of grain bulk to airflow. Greater the porosity, the easier it is for air to flow through the grain, and the higher the velocity you're going to have. And also, of course, because it affects the airflow, it's going to affect the heat exchange during drying and cooling. This next slide shows the typical values for porosity of grains. You can see that for the most part, the grains are in the 40 to 50% porosity range. It can get a little bit higher than that in some cases. But again, it's going to depend on how tightly the material is packed, how it was loaded into the container, and things of that sort. One interesting thing that we've found is that there's actually more airspace in a bin of corn than there is in a large structure filled with potatoes. Even though the air spaces are much larger between the potatoes, there's not as much total volume of air in that type of structure, that type of storage of potatoes as compared to storage of grain in the volume. Coefficient of friction has to do with the resistance to movement of kernels across a surface. If we put some kernels on a flat piece of metal and then began to gradually lift up one edge of that metal so that we created an incline, at a certain point in time the kernels would begin to move over that surface, and that's a reflection of the amount of friction between the grain kernels and that surface. These things affect things like the power requirements for conveying. You can imagine in a auger conveyor or a drag conveyor where we're moving the material along, dragging it across the surface essentially. Greater that friction, the more power is going to be required. It also affects the forces that are exerted on storage structure walls because the kernels are pressed against the wall, and there's a friction between those kernels and the walls, which then affects how the wall itself is loaded. Finally, it's going to affect the ease of unloading a structure. The friction of the kernels with each other, with themselves, is going to affect the flow of the grains, and also, of course, when you're cleaning out the bottom, what's remaining in the bin, the amount of friction involved there is going to affect how easily that material flows out. Let's look, for example, at a truck dump. If we think of the friction between the kernels and the bed of the truck, that's really what's going to affect the angle that we need to elevate that truck to on a dump in order to make sure all the grain flows out quickly and easily from the truck. So it's essentially similar to the problem I talked about before where we had a flat sheet of metal and we elevated to one edge. In this case, we're just applying that same principle or concept to a dumping of a truck. Think of gravity, unloading wagons, and types of equipment of that sort, and this angle of friction, coefficient of friction, is going to be important for those kinds of situations. What type of factors influence the coefficient of friction? First of all, there are material properties. The inherent characteristics of the grains themselves are going to affect the amount of friction. You can think of a grain with a fairly rough surface versus one with a smoother surface. You can think of the cuticle, which is a waxy covering around some of the grains, especially corn. That's going to affect the friction. So the material properties are going to be important, but also the moisture content. You know, just by experience, that grains that are wetter are not going to move as easily along a surface. There's going to be more friction there, more difficult to move that grain. And of course, the type of surface can affect the friction. If you think of moving grain across plywood, especially across the grain rather than parallel to the grain, versus moving across a smooth stainless steel surface, much more friction would be involved with moving the grain. Surface conditions can also affect that. Think of during the winter when it's icy and cold outside, the ice begins to melt and there's a surface film of water over the ice, very slippery type surface, because the surface conditions have changed as a result of the temperature change, the melting of some of the ice. So surface conditions of any type of material can affect that. Other things that might be important would be things like rust or oxidation of the surface. And interestingly enough, you can also have buildup of waxes from the kernels. I mentioned the cuticle in the corn kernel is basically a waxy covering around it. And there was one study that was done where they were doing some measurements on coefficient of friction, and they found that they were changing with time. They got some alcohol, cleaned the surface off, basically removed the wax, and found that the coefficient of friction went back to the original values that they'd seen before. This shows you the effect of moisture content on the coefficient of friction of wheat. Again, a very significant change from 0.32 or 0.33 all the way down to 0.10 as the wheat is dried from 15.9 to 11.2% moisture. And of course, that's going to be true with all of the grains that we're looking at. This shows some of the static coefficients of various grain kernels. Only two are listed here, barley and corn, but there's a fair amount of detail with regard to corn. And you can see that the type of surface that we're looking at really can have a very significant effect on the coefficient of friction. Compare, for example, concrete wood float finish versus plastic smooth finish. You can see a significant reduction in the coefficient of friction there. Surprisingly, the coefficient of friction on wood, Douglas fir, parallel to the grain, is about the same as galvanized sheet metal, both 0.37. A lot of plastics are being used in some of the new handling equipment and storage structures and so on. Polyethylene has about the same coefficient of friction as wood and galvanized sheet metal, but Teflon, which is a very smooth surface type of plastic material, has a very low coefficient of friction. Rubber here, again, you would think that there would be a greater friction with that, and indeed there is. This shows just some more information on other types of material. There's, again, a fair number of different examples included for wheat, just so you can see the effect of the type of surface on the coefficient of friction. Many times when you travel through the countryside during the fall harvest season, during the corn harvest season, you may see large piles of grain near elevators. Basically, they're using just a slab of concrete to store the grain that's overflow. They don't have enough capacity at that particular point in time to store all the grain that they buy, so they can use a temporary storage to take care of the additional requirements that they have. If we want to figure out how much capacity is available in a given size of slab of concrete where we're going to store the grain, the angle of repose is going to be important. And that's basically the angle that the grain makes with the horizontal as it's placed in the pile. There's several different types of angles of repose, two different types. One is for piling or filling. That's the angle formed when grain is allowed to or placed in a pile. It flow out of a spout or off the end of a conveyor and forms a pile underneath that. So the piling angle of repose is for that situation. The other one is the emptying angle of repose, which is what we would get if we remove grain from a bin through an opening in the bottom of the bin. You know that some of the grain is going to remain in the bin if it's a flat bottom bin, and that angle that remaining grain forms with the horizontal surface is the emptying angle of repose. There are several factors that influence the angle of repose. One of these is internal friction, which is the friction between like kernels, one against the other. And moisture content is also going to affect that. Intuitively, you would think that as you increase the moisture content, that angle of repose is going to increase. And that's partially due to the influence it has on the internal friction among the kernels. Particle size distribution can also affect angle of repose. An extreme example, think of corn mixed with fine material. The fine material sort of fills in the pores in between the individual kernels. You can get a steeper angle of repose than if it's clean corn without any fines and all the particles are relatively the same size. Again, the effects of angle of repose are on the maximum depth of something like an outdoor pile where you're storing the grain, and also the maximum height of the peak grain in a storage structure. This shows you some typical values for angles of repose of different grains. There's an average value given along with a minimum and a maximum for each of these. The angle of internal friction has to do with the friction between kernels. So if you have relative motion among kernels, that's resisted by the friction of the kernels on themselves. And the angle of internal friction is the angle whose tangent equals the internal coefficient of friction. So if the internal coefficient of friction were 0.3 or something of that sort, whatever angle would have that number as a tangent would be your angle of internal friction. It's influenced by things such as moisture content, the size and shape of the kernels, and of course it affects things like the angle of repose and also grain flow and the patterns for grain flow in bins. One of the reasons that we're interested in angle of internal friction is that its effect on flow patterns or the information it gives us about controlling the flow patterns in bins. One type of flow that you'll encounter is funnel flow. This is what you'll see if you unload a flat bottom bin from an opening in the center of the bin. Basically, the material begins to flow out of the opening, and just the material above that opening will come out, with material on the top of the bin flowing into that opening or that